Hello viewers, welcome back to the channel, and today we'll discuss the output equation of a synchronous machine. The output equation is the basic tool to initiate the design of a synchronous machine, which relates to the output of the machine with the main dimensions of the stator. Here the output of synchronous machine is equal to Q, which is equal to 3 into VPH into IPH into 10 raised to minus 3, and the unit would be kVA, where VPH is the voltage per phase and IPH is the current per phase. Now let us assume that the induced EMF per phase, which is given by EPH, is equal to VPH, that is the terminal voltage. Moving ahead, the output equation, that is Q, can be further given as 3 into EPH. We have substituted this VPH to EPH, so 3 into EPH into IPH into 10 raised to minus 3 kVA. Moving ahead, we also know that the formula for EPH can be taken as 4.44 into F into T1 into kW into phi. Now this can further be also simplified as 2.22 into F into Z1 into kW into phi. Here what we are doing is, here T1 is the number of turns and Z1 is the number of conductors. So we are changing the number of turns to number of conductors. The winding factors and the flux as well as the frequency remains as it is. Also keep in mind that the number of turns and the number of conductors, the T1 and Z1, are considered in per phase. Now, on further simplifying the equation, the frequency of the generated EMF, the frequency of the generated EMF can also be given by F is equal to P into Ns upon 120, or as P into small ns upon 120, where small ns is nothing but speed of the machine in RPS. This is in RPM and this is in RPS. Further, let us talk about the air gap flux per pole, which is given by phi, and it would be equal to BAV multiplied by pi dl upon P. And talking about the specific electric loading, the specific electric loading which is given by small q is equal to 3 into IPH into Z1 upon pi d. Now, as we had seen earlier, the output equation Q is given by 3 into EPH into IPH into 10 raised to minus 3, and we have seen that EPH is given by 2 into F into Z1 into KW into 5. Sorry, this is 2.22. Again, the IPH and into 10 raised to minus 3 remains as it is. Now we have seen how can F be substituted as well as how can phi be substituted. So we will substitute in this equation. So this becomes 3 multiplied by 2.22. F can be given as P into small ns upon 2 multiplied by Z1 multiplied by KW multiplied by the phi can be given as BAV multiplied by pi dl upon P, and the IPH and 10 raised to 3 remains as it is. So IPH into 10 raised to minus 3. Further solving this equation, we can see this 2 can simplify this and this becomes 1.11. I am clubbing this 3 with Z1 and IPH. We will see that why we are doing this. So what I get is 1.11 into pi dl multiplied by, okay, this P and P also gets cancelled off, so pi dl comes here multiplied by the BAV multiplied by KW and multiplied by the small ns. What I have been clubbing is this 3, Z1 and IPH. So I have 3 Z1 and IPH multiplied by 10 raised to minus 3 comes as it is. Now we have already seen earlier that the specific electric loading Q is given by 3 into IPH into Z1 upon pi d. Now if you look here, I already have 3 into Z1 into IPH. So this can be substituted by Q and the pi d gets into multiplication. So I can write my capital Q is equal to 1.11 multiplied by pi dl multiplied by BAV multiplied by KW multiplied by small ns. This term can be written as Q into pi into d and multiplied by 10 raised to minus 3. Now we already have terms of pi and d, so this could be further clubbed together and we have 1.11 multiplied by pi square d square L into BAV into KW into NS multiplied by 10 raised to minus 3. Now in this equation, I'll club D, L and NS together. So what I'm left in the bracket is 1.11 into pi square into BAV into KW multiplied by D square into L into NS multiplied by 10 raised to minus 3. Now why did we club this together? Because these are the main parameters on which the output is dependent on, where D is nothing but the internal diameter of the stator, L is the gross length of the stator, and as said before, ns is the speed of the machine in rps. Now if I multiply pi square with 1.11, I get the answer as 11 into BAV into KW. I'll also take into 10 raised to minus 3 here itself, and this is multiplied with d square LNS. Now let's name this as a constant. So let us call this as a constant K dash into d square LNS is my output equation, where K dash is nothing but 11 into BAV into KW into 10 raised to minus 3. K dash is normally called as the output coefficient of the synchronous machine. So from this particular equation, we can clearly state that the volume of the machine, that is d square L, is reduced if designed for higher speed, thus decreasing the size and the cost of the machine. The larger the value of output coefficient, the smaller is the size of the machine. And lastly, the output coefficient is larger if the machine is designed at higher specific magnetic and electric loading, which ultimately results into reduction of size and cost of the machine. I hope now you are familiar with the output equations of the synchronous machines and the terms used in this derivation. For any doubts, feel free to comment in the comment section or reach out on the email address provided in the description. Thank you and have a great day.